So I'm not actually going to talk about my research at all. Maybe a brief mention, but I'm going to talk about 2 lessons on time. I'm going to try and be as non-technical as possible and brief on detail, because otherwise my talk on time will not be on time. So, and you. So, but you know, we'll see how we do. Okay. So first, I have a problem for you. So Mario sits here in his Mario Kart. He's stationary. Okay. And he has a shell, a green shell that he can throw at 5 kilometers an hour when he's sitting still in the kart. Then Mario starts driving his kart. I don't know, 50 kilometers an hour seems reasonable. No? Off he goes. Okay. And while he's driving along, he throws the shell. Okay. How quickly does the shell move? You can think about it. I'll give you a couple of minutes. Okay. Okay. So, in the 17th century, when a lot of classical physics was really formulated, Newton defined time in his famous book, the Principia. And Newton's idea of time is that somewhere, God, or the tunable cosmos in this case, as you prefer, has a huge clock, and this clock measures the rate of passage of time. And time is an absolute true and mathematical time of itself, and from its own nature flows equably without relation to anything external. There's a big clock that sets the pace of everything, and everybody abides by this big clock. And everybody can tell what the time is by going to check this big clock. Time is the same for everyone. But a couple of years later, in 1861, Maxwell wrote down this famous set of equations, which you don't really need to understand. But the point is, they predicted that light would exist as a wave and have a definite speed. So if you take the last 2 of these equations, you can combine them in a way that tells you that light propagates as a wave, and this wave has a definite speed. The equations don't tell you anything about the speed of light relative to a moving observer. So they don't tell you anything about how you're looking at the light. They just say there is light and it has this speed. And so this caught the attention of a young man called Albert Einstein in 1905, and he thought, well, you know, there's no reference to any, you know, motion of the observer. So does this mean that light is the same for everyone? Everybody observes the same speed of light. And so in 1905, he wrote down 2 postulates, which evolved into a very famous paper. So the first postulate says that the laws of physics are the same in all inertial reference frames. What does this mean? If I'm moving at a constant speed in a train, or I'm standing still in this room, it doesn't matter. If I do an experiment, I should get the same result. I throw up a ball, I measure the time it takes to come down, I get the same result. There's nothing special about moving at a constant speed. Okay. His second postulate, which was based on Maxwell's equations, he said that the speed of light in a vacuum is independent of the motion of the light source. So again, if I'm standing in a train going at 100 miles per hour and I shine a torch, the photons, or the light that leaves the torch, leaves at the same speed as if I'd shone that torch just standing still. Okay? These don't really seem like great insights, right? He just said that, you know, kind of nothing should change if you're moving or you're not moving. This doesn't seem very profound. But it turns out it is very profound, and it has a lot of interesting consequences that you wouldn't have expected just from these postulates alone. Yeah? So, I come back to the problem I gave you, right? So, really, I didn't pose it all that well, because I asked you what the speed of the shell was, but I didn't say who's measuring the speed of the shell, okay? So now we have Luigi here in the bottom right. And as Mario goes by, throwing the shell at 5 kilometers an hour and moving at 50 kilometers an hour, Luigi watches the shell fly past him, and he sees 55 kilometers an hour, which is just the sum of the speeds. The speed of the shell and the speed of the kart. Okay? Now, let's suppose Mario didn't have a shell, and instead had a torch. Oh, we meant to Photoshop this, we couldn't do it. So this is now, he's throwing a beam of light now, or something like this. He's holding a torch out, okay? And the light is moving at c kilometers an hour. That's what we call the speed of light. It's like 3 times 10 to the 8 meters per second. And his kart is moving much faster now, and his kart is moving at half the speed of light. Okay? What speed is the light that Luigi sees? In the case that it was a shell, we just added the 2 speeds together, right? But Einstein says that we can't do that anymore for light. And in fact, the speed of the shell that Luigi sees is the speed of light again. It hasn't. The fact that Mario is moving hasn't affected the speed of the light at all. The speed of light is constant. It's independent of movement. Okay. This is kind of strange, right? Since normally you can just add velocities as you please. It turns out with light you can't do this. Okay. So, what consequences does this have? So, if we say that the speed of light is constant, then we all know this famous formula. We've all done it at school, I suppose. So, velocity is displacement over time. And we're setting the left-hand side to the constant for light. So that means that the two things on the right-hand side have to change. If one of them changes, then another one has to change in a kind of complementary way in order to make the velocity of light constant. Okay. So we have an example. There is a thing called time dilation. So in these videos, I have two mirrors. I have a particle of light or a beam of light bouncing between the two mirrors. Okay. And in the top one, the mirrors are stationary at rest, as if I'm holding them in this room. And in the bottom one, the mirrors are moving, so I put them on a train, or I put them in Mario's car. Okay, I watch them. Let's see what happens. In the top one, the light has to travel a distance h between the mirrors, but because the mirrors are stationary, it just bounces up and down, and then goes with a certain speed. And it takes a certain time to do it, and the time it takes to do it is related to the distance between the mirrors and the speed of the light, which is constant. In the train's frame, however, the mirrors are now moving. And so if I'm watching this train go by, I see the mirrors move past me, and the light bouncing between the mirrors as they move past me. And so now this means that if I'm looking at the train from the outside, the light takes a kind of different path, right? So as the mirrors move, the light bounces at angles to remain within the two mirrors. Okay? So now this light travels a longer distance. It travels the long arm, the hypotenuse of this triangle, rather than just the straight line, the height of the triangle. Okay? So it travels a longer distance, but we just said the speed of the light is constant, so if it travels a longer distance and it goes at the same speed, then something's going to happen to the time. And we call this phenomenon time dilation. So what happens is the rate of time passage in the bottom is different from the rate of time passage in the top. Okay? And they're related. So T, capital T, is the time that we see in the top frame where the mirrors are stationary. T is the one in which the mirrors are moving, and T0 is the one in which they're stationary. Then T is related to T0 by this little formula, where V is the speed that the mirrors are moving, and C is the speed of light. I put this here because I want to remark on something. You might say, if I have a clock and I'm driving the car down the motorway at 70 miles per hour, I don't see a difference in the time to anyone else. Right? This is I can still arrive at my destination with a time in myself. This formula makes it clear that this ratio V over C has to be large in order for this to make a difference. Because if V is very much smaller than C, then this little V over C term is pretty much 0, and so then T is T0, and I don't notice any difference. This kind of time dilation effect only happens when things are traveling very close to the speed of light, and this V over C term is large, and then I see a noticeable effect. Let's think back to what Newton said about time. This is very different. This says that the time I observe, the time I measure on my watch, is dependent on the speed at which I'm moving. For Newton, time is just something that flows inexorably, and sit there and watch it go. Einstein says that time is different depending on who's measuring it. Your time is no better than my time. The two times are different depending on how we're moving. And what's the point? We can tell exactly how the passage of time is different. That's very good. Another weird thing that happens is called length contraction. So we saw that time.
That's a weird thing.
So we saw that time changes a little, and indeed length changes as well. So if I have my green shell now, which is a length L, and I start moving it at close to the speed of light, c over 3, then this thing is actually going to contract. So although it might be a certain length when it's not moving, when it's moving very fast, the length that you measure of this thing is actually smaller. And again, it's related by this 1 minus v squared over c squared, so this is only a big effect when the velocity is very fast. So not only time changes, length changes. Okay? This is completely counterintuitive. It's Einstein to see this from the principles that he laid out. All this suggests that because space and time are so intimately linked, the fact that the rate at which we move through space changes our perception of time, and vice versa, all this suggests that we shouldn't regard space and time as different things. Space and time should really be put on the same footing, and we call that thing space-time, or space-time continuum, popular science books, but we get fed up with continuums, we just drop the continuum. So, really, space and time should be put on an equal footing. They make one structure that we move through. We move through space-time. So we shouldn't talk about space and time. Space-time is one thing. This is lesson number 1. I have 2. You might object, and you say, you're saying that we should put space and time on the same footing. Really? But it's undeniable, the two are different, right? Because time has one direction. We move through time in one direction. Whereas space, I can move to the left and to the right, and I can move through space as I wish. Time has a kind of arrow, which leads to this famous joke, which I quite like, but you know. So, and we can tell that time has a directionality, right? So, I have another animation. So I have lots of little molecules of gas in a box, right? And I start time evolution, and what happens? All the molecules of gas spread out in time, they diffuse. I can tell the direction of time looking at this video, because what you never see is that all molecules of gas in the room suddenly clump together in the corner, right? If I play this video forwards and backwards, you can tell which way time is going because the reverse never happens. You only ever see things spread out. This is related to an increase in entropy, which is the disorder of things. And so this is one way of defining the flow of time. But in reality, if I looked at only one of the molecules, and I'm going to reduce it to a shell again until I can, and I have a video of my shell moving to the right, if I reverse the direction of time, it just moves to the left again. All the particles in the box, although together they make some complicated motion, the particles themselves are moving in straight lines. And you can't tell whether the straight line, whether I played this video forwards or backwards, whether it was going forwards in time, moving to the right, or backwards in time, moving to the left. Without any prior knowledge, you wouldn't be able to tell. So we call this time reversal symmetry. Okay. So, this is true of classical particles, like my shell, particles in the box or something. And you might say, is it true of everything? Is it true when you look at very small things, when you look at fundamental particles? Is it true that time reversal symmetry is obeyed? As it happens, there is a law that tells us whether or not it is obeyed. But it's called the CPT theorem. So it says that if we apply 3 operations, charge conjugation, we flip all the charges from positive to negative. Parity, we switch our left and right directions, and time reversal, then the whole theory should be invariant under this combination of transformations. So if I assign the number +1 to a case where it's conserved, and -1 to a case where it's violated, then the product of the 3 numbers, C, P, and T, has to be +1. So what are the different possibilities? Either C, P, and T are all conserved, in which case it's just +1 times +1 times +1, you get +1. Okay? But you should also have, T could be -1, for example, and then CP would be -1, and then you have -1 times -1 is +1 again. Okay? So although the theory tells us about the combination of the things, it doesn't tell us about the ones individually. And so it's not immediately apparent that the time reversal property that we saw for the shell is going to be the same for a subatomic body. In 1956, a very clever experimentalist called Madame Wu set out to test whether parity, the P from the last slide, was actually conserved. And she looked at cobalt nuclei, which have a spin. So the arrow in the top panel shows the direction of the spin. So they're going like this, and then there's a right-handed rotation, so the spin is going like this. And the cobalt nucleus decays by missing an electron to the initial one, which you can see at the bottom. And she set up an experiment with cobalt in one configuration, and then she set it up in a mirror world, in which the z-axis, so on the top, the z-axis direction is reversed. The cobalt's rotating the same way, and so the arrow points in the same direction, but now space has been flipped. Okay. If parity were conserved, you would expect equal numbers of electrons to be emitted in the direction of the spin and away from the spin. This is not what she observed. So she had this experiment with the cobalt nuclei all aligned, pointing this way, and then in the mirror world, pointing the same way, as the direction of the spin, and she saw that the electrons were emitted opposite the direction of the spin in the normal world, and in the same direction of the spin as the mirror world. So the mirror world was not the same physically as the original world. So parity was violated. This is a huge thing. That means your left is not the same as your right. If I do everything in the mirror, I mean, on a macroscopic scale, of course it is, but fundamentally, on a very fundamental level, if you look at the smallest particles, the concepts of left and right are not well-defined things, because the left is not the same as the right. You can distinguish between the two. Okay? There was a hope. Now, so we saw that CPT has to be plus 1. Even if P is minus 1, it might be that CP is plus 1. So that if you change the charge and you change the parity, maybe you get the same thing. So if you had anti-cobalt nuclei and they emit positrons, anti-electrons, the antimatter particle, then maybe it would be fine. It turns out this is still not the case, and you still get CP violation in the system. So now we know that C times P is minus 1. So that means that T has to be minus 1, so we have minus 1 times minus 1 gives plus 1. And it turns out that indeed this is true. So there is a particle called a meson, which can exist in 2 configurations, like this. 2 different states. It's kind of, they're related. And as it evolves in time, it can switch between the blue and the red configurations. But it turns out the time it takes to switch from one configuration to the other is not the same as the amount of time it takes to switch back. And so, if I play these 2 videos, you can tell the direction of time from the distance, whether it's long and short, or short then long. So, in fact, these particles break time reversal symmetry. So, what was true for the classical level is no longer true for the quantum level. So time runs backwards. Again, this has enormous implications. I can't begin to explain how profound this truth is. You've related to the fact that time doesn't work the same backwards and forwards, but it turns out that this has a consequence on the amount of matter that's in the universe. At the Big Bang, it's thought that antimatter and matter were produced in equal amounts. But if that were the case, then the matter should have met the antimatter early on and annihilated, and none of us would be here to talk about it. It would all have disappeared. CP violation explains that there's some kind of difference between matter and antimatter, so that we're still alive. So the time reversal implies the CP violation, which implies that we're here. These are very, very profound truths. I think this is really incredible. And so the fact that we're here at all is due to the fact that time reversal symmetry is violated. Okay, so these were my 2 lessons about time. So I had the lesson about space-time and the fact that we all move through time at different rates. Your time is no better than my time. It's just different. And we had the lesson about CP violation and time reversal symmetry. So I hope that was interesting enough for you and comprehensive.